Okay, welcome back to the next lecture here in chapter 5. We're picking up on the exact same slide we left off on. I felt like that was a long lecture that we just went through, so I hope you took some time, kind of looked through it, and now we're going to talk about a few differences between why is it important that we have these chiral compounds. I already mentioned their biological activity. That's sort of like, that's what we're talking about here with enantiomers differ in how they interact with other chiral compounds, and then also their optical activities. So like, so optical activity is the point here. I just want to impress upon you like the importance of this, how they interact with other chiral compounds, because the compounds that make up you and me are chiral, like our proteins, our DNA, our sugars, all of them are chiral. That means that like all of the pharmaceuticals that we use, if they have a chiral center, the orientation of that chiral center is extremely important for its activity. And there's a really famous example here that if you can just like search it as well. It's called thalidomide. Thalidomide was a drug that was used to treat morning sickness in expectant mothers. So pregnant women get morning sickness. They take this drug thalidomide. It's something that was really good at reducing their nausea, which can be really severely debilitating. But it had a chiral carbon in it. And at one point in the chemical engineering of the compound, between when they moved from a small scale to a large scale production, they changed the chemical production process. And what that did is, rather than making purely one version of the compound, it made a mixture of the two versions. Like, so rather than having all R or all S, instead, it had a mixture of R and S of the compound. And while the pure version that they had been testing was really good at this anti-nausea medication, the other compound was actually what's called a teratogen. So it mutates DNA in fetuses, I believe is the case, or it changes the way that a fetus processes its DNA, I should say, to be clear. I'm not 100% certain on how exactly that happens. So what happened is a lot of babies were born with deformities after taking the thalidomide. So if you ever if you're ever in the situation where you're pregnant or your partner's pregnant, you will sign off on these questionnaires that talk about thalidomide for exactly that purpose. Now this happened, I think it was back in the 50s. So most of the babies that were born with defects from thalidomide, that happened in the 1970s, I believe was the case, in the 1950s through 1970s. But it was really a terrible example of kind of the power of chirality and how it interacts with our system. So yeah, just kind of impress upon you that's the case here, and that's why this R versus S configuration is so important. Now, the other ways that they're different is what's called optical activity, and I kind of teased this here at the end of the last lecture, but I can understand if you were a little fatigued and maybe it didn't seem that interesting to you. But yeah, so the thing about light is that we always talk about the speed of light, 3.00 times 10 to the 8th meters per second. Like it's a constant, and it's true in a vacuum. Light always travels at the same speed, but like we don't live in a vacuum, right? I mean, now we breathe in air that's a gas, and gas is mostly vacuum, right? There's little particles bouncing around. Those little particles can slow down the air just a little bit because light can actually get absorbed and re-emitted by electrons, as we've seen before. And so when light passes through a compound or a group of compounds, it's going to hit the groups of electrons there, and it's going to travel differently through that space because that space has a certain electrical charge to it, right? And that electrical charge is going to interact with a photon because photons are little electro and magnetic waves. So that's what we're going to talk about next, which is what's called optical activity. And there's a certain instrument that kind of measures this here. So, okay, so real quick, remember, when you have light, light is usually like oriented in all different directions. But if you have a source of light that is polarized in a single direction, so this is like you take a sheet of polarized paper, and that basically means that only light that gets through is going to be light that like passes through the correct slits. I'm going to have a couple different videos showing you this because this is something that's difficult for me to talk about, without having examples. So look below. I'm going to put a couple other YouTube links below this, and hopefully that'll help kind of show you what that looks like. So yeah, so in this case, it's plane polarized. It's only going in one direction. So you have the electric field and then the perpendicular magnetic field to it. That's an electromagnetic wave, and this is plane polarized. Normal light just goes in all directions around this. So that's the difference here, basically. So now what you can do is if you take a double filter lens, so you take a single filter that gives you plane polarized light. If your next filter is polarized in the same direction, that polarized light passes through, no problem. You still see that light pass through. Now, on the other hand, if you were to rotate that plane, so it's perpendicular, well, the light comes in on this side, it's polarized vertically. This one wants polarized light horizontally. So it's not going to let any of the vertically polarized light through. So now you don't see anything. So this is like your polarized sunglasses and stuff like that. So now the way that we're going to use this basically is we're going to stick one of these compounds that's chiral in between these two filters. And we know that if we have a pure chiral compound, it's going to rotate light one direction or another. So what we can do is we stick the compound in here, the polarized light rotates one way or the other, and we just adjust this filter, clockwise or counterclockwise, and until we actually see the light pass through. And that gives us this optical activity. And remember, only chiral compounds are optically active. All other compounds are symmetrical, so there's no net rotation of the light one way or another. Okay, so this is what a polarimeter looks like. Again, I'm going to show you a video down below, so you can even pause, look at that video. There's a guy that demonstrates what a polarimeter actually, how it works, and it can actually show you what that looks like. Ideally, we would have this in lab, but unfortunately, there's no lab this semester, so this is as good as we can do. So what you do basically, again, you have your light source. Your polarizer initially selects like plane polarized light. And then if you have a chiral compound in here, it's going to rotate the light one way or the other, either to the right or to the left. And then what you do is you adjust this here until you see light on the other end. Okay, so again, watch the video down below. That's going to help you see like what that actually looks like in terms of operation. So now we're going to talk about the numbers that come out of this, because that degree actually gives us a certain number. So, okay, a couple good notes before we move into the actual math. Number one, enantiomers are going to rotate the light to equal degrees, but in opposite directions. So like if the R, for example, rotates the light 45 degrees to the left, then the S is going to rotate it 45 degrees to the right, that kind of thing. Now, this the degree to which it's rotated is going to depend on the concentration. That's going to make sense because the more molecules that the light hits, the more it's going to be rotated. And also the path length. So the path length is like how far does the light have to travel? The longer the path length, the more probable it is to run into one of these molecules. And that's going to cause that rotation. So there's a standard measurement that we use for it. We take 1 gram of a compound dissolved in 1 milliliter of a solution, and with a path length of 1 decimeter for the light. We just pick these standard samples so that we have kind of the same thing going on here. And that actually gives us the specific rotation. And the specific rotation is just alpha in brackets, like here. And the specific rotation, like this, is equal to the particular rotation that we measure, divided by the concentration, times the path length, that's C and L here. This may look familiar from, say, Beer's law, and it is very similar to Beer's law. Now, one thing to point out is that temperature and wavelength also have to be, can also affect this. So we have to specify the temperature that we're going to measure it at and the wavelength of light that's also measured. So we just kind of like note that here. Yeah, so that's also part of the measurements that have to be taken. Okay, so for example, if we have bromobutane, we have we have R2-bromobutane and we have S2-bromobutane. So if we take a pure sample, 1 gram, so if it's 1 gram per 1 milliliter with 1 decimeter of light, that is going to rotate a plane polarized light negative 23.1 degrees, so to the left. On the other hand, if you have S2-bromobutane, that's going to do the opposite. It's going to move it to the right, plus 23.1 degrees. And again, that you can think of it as degrees, like you're moving the little polarimeter one way or the other. You move it to the one way, that's the positive. You move it to the other way, that's the negative. And that's the positive and negative that we get here. Now, what we want to point out is that there's no correlation between RS and plus minus. The plus minus are measurements that we take in lab. And you can't say that, oh, this one's an S and it's plus, and this one's an R and it's minus. That does not happen, okay? So don't even think that. Oh, right, so that's the one thing we don't wanna like get that confused. If you have this plus rotation, that's what we call dextro-rotary. So if you're up on your Latin, that's dextro is to the right, dextro-rotary, and then minus is levo-rotary, that's left, levo-rotary to the left. So that's just one way you can say, oh, this is dextro-rotary, it's got a positive specific rotation. It's levo-rotary if it has a negative specific rotation. And just to kind of like emphasize here, so this is an S-configured compound. Its optical rotation is negative, so it'd be levo-rotary at 20 degrees Celsius, but it's actually positive at 100 degrees Celsius. So if you change the temperature, it goes from levo to dextro-rotary. So just keep that in mind. Again, R and S, plus and minus, there's no correlation there. Yeah, we don't have any way of predicting the optical activity. You just have to measure it experimentally. So, however, we do know that if you have exactly a 50-50 mixture of the two compounds, so the R and the S, this is what we call a racemic mixture, a mixture of two enantiomers. The rotations essentially cancel each other out. So you have one that may be dextro-rotary, the other's levo-rotary. If you have the same concentration, the light's going to eventually be rotated the same way. So this racemic mixture is going to have an optical rotation of 0 degrees. We're not going to see any change in the light. It's only when we have one enantiomer present in excess that we're going to have an actual optical rotation. And keep in mind, if you still have some of the other enantiomer, that's going to counteract the more pure enantiomer. So you won't get the full optical rotation of the pure enantiomer. Okay, so here's our math slide here. So what we're going to do is we're going to be able to calculate the percent enantiomeric excess based on the optical rotation. So here's going to be our question. Suppose a mixture of R and S to a specific rotation of negative 4.6 degrees. This allows us to determine the percent EE. Now we know that the percent enantiomeric excess is going to be equal to the observed specific rotation divided by the specific rotation of the pure enantiomer times 100%. Now, we see here that we've got R and S. R is the negative 23.1, and the S is the positive 23.1. Now, if we have a specific rotation of negative 4.6 degrees in our sample, which is a mixture of the two, which one are you going to have more of? Which one do you have more of? So remember, if it's a 50-50 mixture, optical activity is going to be 0. So if it's negative, that we're measuring here, that means that we must have a little bit more of the one that's negative, in this case, the R-bromobutane, rather than the S-bromobutane, which would have a positive effect if we had that one. So now, because we have this number here, now we're able to calculate the percent enantiomeric excess. So that's the percent enantiomeric excess that we can calculate here. So all we have to do is just plug that number in. So let's go ahead and add some text here. So the percent enantiomeric excess is going to be equal to the observed alpha, that's negative 4.6 degrees, divided by the alpha of the pure enantiomer, the optical activity, that's negative 23.1. And then it's a percent, so it's times 100. So it's going to look like that. We go ahead and do the math here, and we get 20% enantiomeric excess. And in particular, what we're saying is we have 20% enantiomeric excess of the are enantiomers. Now, here's a fun question. What if we put it this way? What percentage of your mixture is R versus is S? What this says is if you have 20% enantiomeric excess, that means that you have 20% more of R than S. And then maybe it makes more sense if we put this in terms of mathematical terms. So in other words, your percent R is equal to your percent S plus 20. So we know that. And what's the other thing that we know that we can say about the relationship between percent S and percent R? I'll let you think about it. Well, the other thing we know is that the mixture has to be 100%, right? So percent R plus percent S equals 100. So now with these two equations, we can actually solve for the percent R and the percent S. So what I'm going to do is I'm just going to do a substitution. I'm going to take, oh yeah, it never lets me do this, but I'm going to take percent S plus 20, and we're going to substitute it in for percent R. So then that gives us percent S plus 20 plus percent S equals 100. Easy enough, right? So then it's 2 times percent S plus 20 equals 100, just like that. So now all we have to do is solve for percent S. Percent S then subtract 20 from both sides, divide by 2. That's going to be equal to 40%. Now we have percent S. We know that percent R equals percent S plus 20. So percent R equals 40 plus 20. So it equals 60%. So we know that our sample is 60% R, 40% S. Go ahead, we've got a bunch of sample problems. I recommend pausing the video, looking at those sample problems, and working on those now. Okay, all right, so in review, real quick, we want to talk about a different type of stereoisomer relationship. So you have isomers, you can have constitutional isomers on the one part, that's what we covered in the last chapter. Then you have stereoisomers, that's what we're talking about now. Now we have two subcategories of stereoisomers. We have enantiomers, which are the non-superimposable mirror images. That's mostly what I've been talking to you about so far. But we also have diastereomers. Diastereomers, we know, have to have the same connectivity, same molecular formula. So the thing is here, sometimes you can have things that are non-superimposable that have the same connectivity, but they're not mirror images. We're going to go over a few examples of that here. So remember, enantiomers are non-superimposable mirror images. Diastereomers, non-superimposable stereoisomers that are not mirror images. And there's a simple way to come up with this, which is basically, what if you have more than one chiral center? That's what we're going to talk about now. So here, for example, cis-2-butene and trans-2-butene. These are stereoisomers, yet as you can see, they're not mirror images of one another. So we would call these diastereomers. Enantiomers have the same physical properties. Diastereomers have different physical properties. So in order for your enantiomers to have the same physical in order for your stereoisomer to have the same physical properties, it's got to be an enantiomer, an exact mirror image. And what that really means is that each of the stereocenters in a given compound, in each of the chiral centers, has to be flipped. So like, for example, if we have a cyclohexane that's substituted with a chlorine, a methyl group, and a hydroxyl group, or an alcohol. If you have 1R, 2R, 3S, its enantiomer has to be the opposite. It has to be 1S, 2S, 3R. That's the only way for this to be an enantiomer, and that's the only molecule that's an enantiomer. But rather than flipping all three of these stereocenters, what if you flip one at a time? Like, let's say chlorine, we take the methyl group and we flip it down. That gives us this here. Well, these are not mirror images, right? They've only got one of the stereocenters flipped. So it's 1R, 2R, 3S versus 1R, 2S, 3S. So only the second carbon's been flipped. Well, this is a very important difference. where now all of a sudden this relationship is not enantiomeric. This is what we call a diastereomer. I hope that makes sense. So the way you can think about it is like it's a family that's got 4 sets of twins. The twins are the enantiomers. They're exact mirror images of one another. But they're all siblings to one another. In other words, they're all diastereomers of one another. Yeah, sorry, I stole that example from your book, so there you go. Okay, so now the total number of stereoisomers, so enantiomers plus diastereomers for a compound, is only dependent on the chiral centers in the compound. So if I ever ask you this question on the test, what is the maximum number of stereoisomers for a particular compound? All you do is you count up the number of chiral centers, then you take 2 and raise it to that power n. So like if something has, easy enough, if something has 1 chiral center, you know it's that molecule and it's an enantiomer. That's 2 to the 1, that's 2. Great. Well, if you have 2 stereocenters, now it's 2 squared is 4. So let's go ahead and take a look at an important biomolecule, cholesterol. Looking at cholesterol, how many possible cholesterol isomers are there using this formula? Go ahead, pause the video. When you come back, I'm going to have circled the stereo centers, and then from there, we will go ahead and do the math. So give it a shot. Okay, so let's go ahead and count them up. So we got this one here, 1, 2, 3, 4 different groups. 1, 2, 3, 4 different groups. So 1, 2, 3, 4, 5, 6, 7, 8 possible stereoisomers. That means that our total number of stereoisomers, so 8 different chiral centers, that means our stereoisomers is going to be equal to 2 raised to the 8. And I should have done this on my calculator beforehand, but I got my calculator right here. I know you haven't had to use your calculator a lot this semester, but it's time. So 2, y to the x, 8, 256. That makes sense. I probably could have known that one. So we have 256 possible stereoisomers. And again, you can follow along in your book. That's Skill Builder 5.6. Okay, now the last point here is that not all things that look like they're chiral are chiral. And the reason for that is if you have a compound that appears to have 2 chiral centers, but possesses a plane of symmetry, that is actually what we're going to call a meso compound, because as we're about to see, it's not truly chiral. So for example, we've got trans 1,2-dimethylcyclohexane versus cis 1,2-dimethylcyclohexane. In this case, the trans isomer does not have a plane of symmetry. So they both would have 2 chiral centers based on what we counted up before. The trans isomer is indeed chiral, like what we would suspect. But if we look for example, we stick our 1,2-dimethyl, the cis isomer, into our polarimeter, like what we were looking at before, we actually find out that it doesn't rotate light at all. There's no optical activity in it. And the reason for that is that it actually possesses a plane of symmetry. So we draw the plane of symmetry this way. Because both of these methyl groups are pointed up, we see that internally, if we reflect this carbon onto this carbon, 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 it's like self-superimposable in a way. So in this way, because it's superimposable on its mirror image, it's not a chiral compound. I know that seems crazy, but this is something that we need to identify before we kind of move forward. These are what we call meso compounds. And the easy way to see if a compound is meso is just see if that compound is identical to its mirror image. We could easily do that here because as we can see, this is a cyclohexane with the 2 methyl groups pointed up like that. Imagine a cyclohexane with 2 methyl groups pointed down. Well, you can just superimpose them by flipping one onto the other. So next up, if it has a plane of symmetry, it's achiral. But that said, a compound that lacks a plane of symmetry can still be an achiral compound because it could have reflectional symmetry through an inversion if it can be inverted through a central point in the molecule. So here you would think, okay, looking at this carbon and this carbon, they're both chiral, right? They would look like they're bonded to 4 different things. But if you pick a point and then invert the molecule through that point, So this one right here. So we're going to invert the molecule on itself. So this one starting up, this carbon going up, that becomes this methyl group coming down. This methyl group coming down becomes this one coming up. This methyl group sticking out over here becomes this methyl group out here. This nitrogen becomes this nitrogen. This carbon becomes this carbon. This carbon becomes this carbon. This oxygen becomes this oxygen. This oxygen becomes this carbon. It inverts exactly on top of itself. That's a different type of symmetry. That's called an inversion symmetry. And because of that inversion symmetry, it's actually achiral. Another way you can think about it is like basically when you're looking at like 4 different things that are bonded to one another, because these carbons are essentially the same, they end up just being achiral through that inversion point. So summing up, now that's a rare thing that you're not going to run into much until you get into inorganic chemistry, but it is relevant. So like, for example, like on the test, I may ask you, why is this compound achiral? Well, you're going to have to look at symmetry to tell me that. I'll try to give you a hint in the right direction when it comes to that. Okay, so here we go. So remember that rotational symmetry is not important to chirality. If you have a compound that has a plane of symmetry, that's achiral. And then oftentimes a plane without a compound that has a chiral carbon without a plane of symmetry is usually chiral, except for certain other symmetries like an inversion center. So kind of a minor point. Now, if you have a compound that has chiral centers but is achiral because of that symmetry, this is what we call a meso compound. These down here are all meso compounds. And the easiest way to identify meso compounds is just draw the enantiomer of it, okay? So that even works actually if you go here, draw the enantiomer of this one. Well, as it turns out, it's actually superimposable on itself. So when you draw the enantiomer of these, like here's the bromine going down, the bromine going down, well, you can just take that cyclohexane and flip it. Practice around with that, and then you'll just notice that these meso compounds do not have the same number of stereoisomers as you would expect. So keep that in mind, and I think with that, that covers this part of the chapter. We're going to move on, and we're going to talk about some other types of stereoisomers. I think we have a small lecture on Fisher projections next. So take some more practice in the notes down below, and ask your questions in the comments, and I will get back to you as soon as possible. See you.